So while I'm out today, we're going to talk about something called the heat equation. It's involved in the transfer of energy in a sample of matter when the temperature changes. So you do need to take these notes in your notebook. So you may need to get that out. And I want you to write down the notes and a couple of sample problems so that when you're going through your homework, you'll be able to answer the problems by going back and looking at your notes. So first of all, we see in the box here the heat equation, Q equals mc delta T. The heat equation involves four variables. Q, which stands for thermal energy or heat energy that's transferred in or out of an object when it changes temperature. M stands for mass, and for this class we'll mostly use grams for mass. C is the newest, most unusual thing for most students, and that is the specific heat. The specific heat is the amount of energy required to change the temperature of a substance by 1 degree Celsius. So it has this weird unit, joules per gram degree Celsius. In the table, we see some different specific heats. So just like density, specific heat is an intensive property, and each substance has its own specific heat. So for aluminum, for instance, it's 0.899 joules for every gram degree Celsius. So if you had a 1 gram sample of aluminum and you wanted to change its temperature by 1 degree Celsius, you would have to add 0.899 joules of energy to it. If you wanted to change its temperature by 2 degrees Celsius, you would just double that. So it's just an amount of energy required to change the temperature by 1 degree Celsius for a 1 gram sample. And then finally we have delta T. Now delta T is technically two symbols, but it really stands for just kind of one quantity, which is the change in temperature. So if something is at 10 degrees and it jumps up to 15 degrees, its change in temperature was 5 degrees. One thing that sometimes can be important is if something releases energy, its temperature might drop. So if you had like a hot piece of metal and it cooled down, energy would be released from it as it cooled down, and so it could experience a negative delta T. For the most part, we just need to think about the delta T as the overall change in temperature. And then you can just decide if energy is absorbed, if it heats up and increases temperature, or that amount of energy is released if it cools down and decreases in temperature. It's important to pay attention to the units when you solve these problems because the units are going to help you to figure out what numbers to plug in where into the equation. Oftentimes students mix up Q and C. Q is the amount of energy itself, which is just joules. C is the specific heat, so it's a number that's locked in for each sample. So you'll have a table like the blue table on the right side of the screen there. You'll always have a table that will help you figure out what the specific heat of a substance is when you're solving these problems. So if we just look at a few values of specific heat, we can see we've got aluminum, brass, copper, nickel, iron, steel. All of these are, except for metal, all of these, except for water, all of these are metals. You notice that the metals have relatively low specific heat values. Having a low specific heat value makes something a good conductor of heat. Water has a high specific heat value, and so water is thought to be maybe a better insulator than some of the others like the metals. And I think of specific heat as kind of the cost to heat something up. So if you wanted to heat up a piece of brass, for example, it's relatively cheap. It doesn't take a whole lot of energy to heat up brass by 1 degree Celsius. It only takes 0.38 joules. But to heat up water by 1 degree Celsius, it takes a lot more energy. It takes 4.1 joules for every degree Celsius. So you can think of it as almost the cost in energy to change something's temperature. All right, now we'll just practice with that equation and some sample problems. So it's helpful when you're thinking about these questions to have the equation written down. So if I just go ahead and write this equation that I'll be using today, Q equals mc delta T, that's going to help me keep up with all of these variables. So the question says how much heat is absorbed, so heat would be the heat energy. So I can already tell that I'm looking for heat because it says how much heat or heat energy is absorbed when 8.0 grams, okay, that would be a mass if it's in grams, of water increases in temperature from 30 degrees Celsius to 40 degrees Celsius. So what we're interested in here is the change in temperature. Well, the change in temperature, if it goes from 30 to 40, the change in temperature was a 10-degree Celsius temperature change. So you'll have to be sure you use the change in temperature, maybe not necessarily the exact temperatures that are given, but just subtract them, 40 minus 30, and there's your change in temperature. To find C, you'll probably want to, when you're working on your homework assignment, you'll have this table. And this table has some specific heats of all sorts of different materials because this question is about water. That's why we go to our table and we look for water, and it tells us that the specific heat is 4.184 joules per gram degree Celsius. All right, now that we've got all those values laid out, we can just plug into our equation. Mass is 8.0, and this is the part that you'll have to show on your homework. You'll have to show how you're using the values in the equation. C is 4.184. Joules per gram degree Celsius. And finally, my temperature change was 10 degrees. So then I can just grab my calculator and multiply those. And I got 334. Based on my numbers that I have so far, I should probably just keep 2 sig figs. So first I'll write down what my calculator tells me. But then I realize I just need the first 2 sig figs. All right, so the 4 tells the 3 to stay a 3, and I'll just round that to 330. And then I found energy, so it's going to be joules. Also, you'll notice in the question, grams and grams, or in the problem that I solved, grams and grams canceled. Also, degrees Celsius canceled with degrees Celsius, so all we're left with is joules anyway. Okay, so in this one, we just solved for Q using the equation. Maybe the most important thing that you may have picked up on was that we had to find the change in temperature. It changed by 10 degrees when it went from 30 to 40. So that's what we use in the calculation. All right, sometimes you might be solving for something other than Q, and that's what we're going to see in this problem. It says a hot piece of iron with a mass of 20 grams cools down. What is the temperature change of the iron after it has released 500 joules of energy? So a couple of different things about this one. First of all, it's about iron. So if we know it's about iron, that means we have to use iron-specific heat, which is in this table. It says it's 0.449. So sometimes people like to lay out all of the variables just like this and plug in as they go. So we said we're dealing with iron. So iron has the specific heat, that's C, of 0.449. Joules per gram degree Celsius. The problem tells me that I have a mass of 20 grams. Okay, so that's my M, my mass. That decimal just gives me an extra sig fig there. And then it tells me it has released 500 joules of energy. Okay, 500 joules. That means I'm going to put a 500 here. Now, if an object releases energy, that means that it has a negative value for Q. Okay? That we can also think of that as, that means the temperature is going to be decreasing for it. But in terms of the math, it is helpful. When you see released energy, we can put negative there for 500 joules. If it had absorbed the energy, that would be positive 500. In the end, we know that if the iron's cooling down, it's going to experience a decrease in temperature, so a negative temperature change. So as long as we keep up with that, it's kind of okay not to worry about Q being positive or negative in the end. All right, so if we plug in as we solve this, again, I'm still using the original equation, Q equals mc delta T. But this time for Q, on the left, I'm going to plug in negative 500. For my mass, I've got 20 grams. For C, I'm saying 0.449. And then I'm trying to find the change in temperature. So delta T is my X. If I just want to call it X, that's what I'm looking for, my change in temperature. Then I've got to solve this for X. Just to save a little space here, I'll wait and just plug in my unit at the end. All right, so I could go ahead and just simplify the right-hand side and say 20 times 0.449. I got 8.98. Times X, where X represents my change in temperature. Now I'll divide both sides by 8.98. All right, they cancel on the right. And then I'll do 500, or negative 500, divided by 8.98. And I got negative 56 degrees. So that means my change in temperature, so I can call it delta T now. My change in temperature is negative 56 degrees. So this piece of iron, when it lost 500 joules of energy, its temperature went down by 56 degrees Celsius. All right, so that summarizes two sample problems. You may have some others where you're using the heat equation to solve for C, but it's the same idea. If just like we did on the left-hand side of this screen, you just lay out Q, M, C, delta T, put down the 3 of the 4 variables that you know, and then just call the other one X and solve for it. You should be in good shape. Be sure to think about your units at the end. If it's Q, the unit's going to be joules. If it's a specific heat problem, the unit's joules per gram degree Celsius. If it's a temperature question, it's going to be degrees Celsius. And if it's a mass question, it will be in grams. All right, good luck on your assignment. Be sure to show your work and do your best, and we'll and have a good day. Thanks.